So hello everyone. So today we shall see the reconstruction of band limited signal from its samples. So we have discussed about this quite a lot in the previous lecture where we have seen the Nyquist-Shannon sampling theorem, where it says that if the Nyquist sampling theorem, whatever the conditions are in that theorem are met, plus we have the modulated impulse train filtered with the low pass filter, then whatever be the output you would get, let's call it a filtered output, then the Fourier transform of that filtered output would be equal to the Fourier transform of the continuous time signal. What we meant to say, that if the Nyquist sampling theorem conditions are met, plus you have the modulated impulse train signal impulse train signal filtered with the low pass filter, right? If you have both these two things, then whatever be the output you would get, or let's call it the filtered output, then the Fourier transform of this filtered output would be equal to the Fourier transform of your XEFT. So this is how we have seen the reconstruction of the continuous time signal from the from its samples, right? But go a bit we'll dwell a bit into it, that what are the other implications of the reconstruction, what are the properties of this low pass filter, and where, yeah. So let we have x of n, which is now given to us. Okay, so from this xn, what we want to do, given this x of n, okay, let's call it the D to C converter, and from here we want to reconstruct continuous time signal, let's call it the reconstructed signal as xr of t. Okay, so we will now see what are the different blocks inside this D to C converter, and what are the basic mathematics behind constructing xr of t from its samples xn. Okay, so given this x of n, first of all we will create an impulse train, let's call it x s of t, which we form as n minus infinity to infinity x of n del t minus nt. Okay. So from this x of s, you notice that the nth sample of the sequence is associated with the impulse at t is equal to nt only, right? Otherwise it is 0. So having computed this, the impulse train x of s, we will pass this signal through an ideal reconstruction filter whose impulse response is given by, let's say, hr of t. Let me draw the block diagram so that the things would become a bit clearer. So now we are opening this block D to C converter, that what are the different components inside this block. So we have x of n. Okay. So from this x of n, first of all we convert the sequence to impulse train, which is have the sampling period capital T. So note this block, because we will come back to this block once again when we see the frequency domain analysis of this overall reconstruction thing. So this generate your x of t. Now we will pass this x of t to an ideal reconstruction filter, let's call the HR of j omega, which would be in continuous time. Okay, and this will give us the signal XR of t. So these are the two cascaded blocks inside this T to C converter, which gives you XR of t, and we call it the ideal reconstruction. Okay, so looking at this block diagram, what we have that your I can represent my XR of t as, again, I have implicitly used the property of the impulse function, so that I can write XR of t as the summation over n minus infinity to infinity of x of n times HR of t minus n capital T. Okay, where we have this ideal reconstruction filter. So one of the filter we have seen in the last couple of classes is your this one HR of t, where you have this minus pi by t and pi by t with the gain t, and this is your HR of j omega, and you have this omega. Okay, so this is the filter we have been seeing earlier. Now we will see a bit into that what it actually gives us to us. Right? So this, we define this as an ideal reconstruction filter, which is having a gain t. This is to compensate the factor 1 by t we obtained in the previous step. It has the cutoff frequency, which is omega c, lying between omega n and omega s minus omega n. Okay. So the convenient choice for selecting this cutoff frequency omega c is most of the time your half of the sampling time, which is pi by t. So that's why we have used this minus pi by t or pi by t. Okay. If I take the Fourier inverse of this HR of j omega, then you would get a sin c function, which is something like this one, minus t and capital T, and the next one you get at 3t, and similarly. This is the ideal filter response in the time domain, where you have this HR of t with the x-axis time t. Okay, and the mathematical representation of this signal HR of t is sine pi t by t and pi t by t. This you can also compute by yourself by computing the Fourier inverse of this frequency domain representation of the low pass filter, the ideal low pass filter. So substituting this HR of t here, we can represent your XR of t as the summation of n minus infinity to infinity xn sine pi t minus nt by t divided by pi t minus nt by t. Okay, so this is the main equation for computing your reconstructed for reconstructing the original signal XC. Okay, so there are some important points to note from this equation. So if let's rewrite this equation XR of t in terms of HR and Xn, and minus infinity to infinity Xn HR t minus nt. So if you closely look at this equation can be visualized as the continuous time signal in terms of a linear combination of this as a basis function with the samples x of n playing the role of the coefficient. Let me write this equation by explicitly writing this summation. So your xr of t is let's say plus x of minus 1 hr t plus capital T plus x of 0 in hr of t plus x1 hr t minus capital T plus this thing. Okay, so it would be a infinite sum. So this can be represented into the multiplication of two vectors. So let's organize all these impulse responses in the row vector as hr t plus capital D, HRT and HR t minus NT and so on, multiplied by x of minus 1, x of 0, x of 1 and so on. Okay. So this you will notice that this straight away forms as the basis for computing your x's of t, and this represent in fact this is a representation because this is fixed. The samples are fixed. So for different bases you can compute this xr of t. And in fact there are many choices of the basis functions. So there is one interesting I would say the review article. So I will upload this review article on the Google Classroom page. Okay, so you can see that what are the various types of basis function you can use to reconstruct the signal, the continuous time signal, given the sequences. Okay, but your hr of t is sine pi t by t, 1 pi t by t, and xn are the natural basis functions and coefficients for representing the band limited continuous time signals. Okay, so if we see from the frequency domain arguments to see some interesting points. So from frequency domain arguments, which we had seen in the last lecture, we saw that if xn is equal to xe of nt, where your xe of j omega is equal to 0 for omega mod omega greater than equal to pi by t. Okay, this is the property of the band limited signal. Then the reconstructed signal xrt is equal to your xe of t. Okay, so this is not immediately obvious. It is not immediately obvious that this is true the by considering this equation alone. What we have observed in the frequency domain in the last lecture. So let's see that what this analysis give to us. So hr of t is sine pi t by t and pi t by t. Okay, so if I see that hr of 0 computing from L'Hopital rule, it would be equal to 1 if you compute the limit as t tends to 0 for this hr of t, and your hr for nt, if I substitute uh, t small t is equal to n times capital T, so you would obtain sine n pi over n pi. So this would always be 0 because n is an integer. So it would be 0 for n is equal to plus minus 1 or plus minus 2 and so on. Then And from the above, this is condition is given to us that if your x of n is equal to xc of nt, then let's write this first of all xr. So we shall write xr at some m times t. Okay, so xr m of t, which we had seen from this formula, substituting t is equal to mt, you would get summation xn sine pi m minus n t by t and pi m minus n t by t. Okay, so this t would cancel out and the remaining part is x of n sine pi m minus n and pi m minus n. So when we are writing this m times c, m is already an integer. In that case, m minus n would always be an integer. So in that case, this term would be equal to 0, except when you have m is equal to n. Okay, so here we shall replace it by m is equal to n. So in that case, your xr of m times t would in fact become equal to xm, because there is no longer t, since t is cancelled out. So we can remove this t, xm, and it would be equal and for except at m is equal to n, otherwise it is 0. So it would be equal to xc mt for all integer m. So the important point to see here that the reconstructed signal has the same value at the sampling time as the original continuous time signal, and it is independently of t, because whatever be the conditions of the Nyquist sampling theorem were already considered above, right? Okay, so if there is no aliasing, then you can exactly construct the continuous time signal from its samples. Yeah? So if we see this thing uh, in the frequency domain, meaning to say, yeah, this one. If I take the Fourier transform of this equation, what you will get that xr of j omega would be equal to n minus infinity to infinity x of n hr j omega and e to the power minus j omega t. Okay, this we had seen many times in the previous classes, so you can directly write this by taking the Fourier transform of that signal. Okay, since we are taking summation over n, so this part can come outside of the summation of this summation. So I can write this hr j omega as summation n minus infinity to infinity xn minus j omega t, and this is nothing but the Fourier transform of hr j omega, Fourier transform of x e to the power j omega t. Okay, this is what you see in the frequency domain. So one important thing to note here, that this x e to the power j big omega t is in fact is the frequency scaled version of e to the power j omega, which is the discrete time Fourier transform of x of n. And this we have obtained this omega t when we went from sequences to the impulse train that causes omega to be replaced by this big omega t. Okay, so this is one interesting property to see in the frequency domain. and I think we can stop here for today. Okay, thank you.